Let's solve this problem, guys. So we have two sequences an and bn. So an is given as the greatest integer function of this n squared by n plus 1, and bn is given as that sequence minus this greatest integer function. So let's call this, since both of them are dependent on this unique sequence, let's call it Cn is equal to n squared by n plus 1. Now observe that we are required to find the convergence of both an and bn, and it is dependent on Cn. So let's first understand the where Cn converges to. So Cn converges to infinity. So we will because the numerator is a quadratic with positive coefficient, and denominator is a linear with a positive coefficient, so it goes to infinity. So now the question is that how do we proceed to solve this problem? So to do that, let's revise a bit of the theory about the greatest integer function and the fractional part. Now observe that if x is a number, and if you take the greatest integer function of that x, this one, then observe that this greatest integer function is of course less than equal to the x, but it's also greater than x minus 1 because it's just the closest possible integer to x. And also the fractional part is nothing but x minus the greatest integer function of x. Also remember that this fractional part is between 1 and greater than equal to 1 and less than greater than equal to 0 and less than 1. Now observe that, now let's use these inequalities here, because understand that one great way to find the limits of functions or sequence, it's always to use inequalities to find, so that you can apply sandwich theorem. Okay, so observe that using this basic result of the greatest integer function, you can get that an is less than equal to Cn and greater than Cn minus 1. It will be just greater than Cn minus 1. And by sandwich theorem, you already know that Cn is going to infinity. So by sandwich theorem, since both of them are going to infinity, Cn minus 1 and Cn, an is also going to infinity. Okay. And now for the bn part, remember that bn is between 0 and 1. So bn is not divergent in that sense. It will never be divergent to infinity. Okay, because it's always bounded. Now let's understand the behavior of bn. Now bn is a fractional part of this number, right, of this sequence, of this function. So the trick here, the hint here is always when you're calculating the fractional part, take out the integer part from bn. Okay, so we can easily see, we know that n square minus 1 is divisible by n plus 1. So we do that, we take that part out, and we are left with this integer n plus n minus 1 plus this extra term 1 by n plus 1. Now since it's a fractional part, this n minus part will go away, and we will be just left with the fractional part of 1 by n plus 1. So observe that since it's this 1 by n plus 1 is less than 1 for n greater than equal to 1, bn is nothing but actually this value. So we can actually say bn equal to 1 by n plus 1, not just less than equal to. And because 1 by n plus 1 is less than 1, and hence you can say that bn is going to 0 because this is converging to 0. This is just sandwich theorem, but actually bn equal to 1 by n plus 1. This is a generalized thing, which is also true, but bn exactly is equal to 1 by n plus 1. So this is the solution, guys. It's very easy. An is diverging to infinity and bn is converging to 0. Now food for thought question for you is that if Cn was, instead of n square, just n square, if it was a general quadratic an squared plus bn plus c, where a, b, c are positive integers, then what will be the solution? Whether it will converge or whether it will diverge, for what a, b and c it will converge, what is the behavior of this an and bn for this general a, b, c, and if bn converges here also, then for which values of a, b and c it will converge. So try to find this out, try to solve this problem. I will see you in the next video. Bye bye.